This is a lesson for pre-calculus for section 5.3, and it is day 1. And we're going to talk about sum and difference identities today. Our objective is to be able to understand and use the sum and difference formulas for sine, cosine, and tangent. So yesterday I was showing you the big long list of all the wonderful identities that we can get by proving from one of the things we do know two new formulas. And that means we're going to take those steps to get those formulas the way that we did the last couple of sections. But what we're going to kind of step off with right now and step, I guess, to the side a little bit is using them. I mean, once you have them, you want to be able to use them. So for a little bit, we're going to talk about these formulas and how they could be used to find different values that aren't necessarily something that's easy for us to find. We know that easy things to find would be the 30, 60, 90, 45, 45, 90 triangles, those special right triangles, but our job is to figure out others that could be perfect answers, because math is about perfect. We want those elegant answers whenever we can get them. So wouldn't it be nice if every function followed this rule, that if you want f of u plus v, all you have to do is add the two function values together. That's it. I mean, that would be a great little world. It doesn't work that way. So like it says, we know that is not the case. For example, the quantity u plus v squared does not equal u squared plus v squared. And that's because the 2 that we have for a power here for our exponent cannot be distributed in those parentheses because there's addition in there. So what really happens is we end up using u plus v times u plus v because powers go to the closest thing to their left. This 2 is actually for those parentheses. It means they want 2 sets of parentheses there. And that will definitely not give us u squared plus v squared. Likewise, if we have the square root of u plus v, that is not the square root of u plus the square root of v. You cannot separate those two. And if you're thinking, well, that should work, then go ahead and put in a couple of nice numbers like 9 plus 4. You know, that's the square root of 13. But if we take the square root of 9 plus the square root of 4, that's 3 plus 2, which is 5. And the square root of 13 would not give you 5, so that doesn't work. And we know those don't work, so we know in advance that there are cases where trying to break things apart like this is not a good plan. It isn't going to work. So down below, we see an exploration where it says, let's get past the obvious but incorrect formulas. And number 1 says, let u equal pi and let v equal pi over 2. So start thinking about my unit circle right away. Oops, my arrow's kind of in the way of that one. Let's just do 3 pi over 2 a little bit separate here. So now I have my unit circle up there where u is supposed to be pi and v is supposed to be pi over 2. It says find the sine of u plus v. Okay, so we want the sine of pi plus pi over 2. Well, pi, if we slap a 1 underneath there, would need a common denominator, so we multiply the top and the bottom by 2, and we have 2 pi over 2 plus 1 pi over 2, which would be 3 pi over 2. And if we want the sine of 3 pi over 2, we come down here and realize, well, the coordinates we would use on the unit circle would be 0, negative 1. So the sine of 3 pi over 2, let me put that SIN in front of that, would be negative 1. And then it says, you know what, let's just find the sine of u, figure out what it is, and add that to the sine of v. So the sine of pi plus the sine of pi over 2. Well, the sine of pi is 0. The sine of pi over 2 is 1. Remember, it's always cosine, comma, sine as an ordered pair. And 0 plus 1 equals positive 1. So the sine of u plus v, in parentheses, grouped together, does not equal the sine of u individually plus the sine of v. So to answer their question, does that make them equal? No, it doesn't make them equal. That's not going to work. So we can't use pi and pi over 2 as a combination to add to get the 3 pi over 2. That it just doesn't work. Now for number 2, it says, how about if we have u as 0 and v as 2 pi? Okay, so maybe it was just those were two really bad quadrantal angles. Maybe the other two will work nicer. So we're supposed to find the cosine of 0 plus 2 pi. Well, that's going to be the cosine of 2 pi. And remembering again that it's always cosine comma sine, that would be a 1. And then they want us to find them individually. So the cosine of 0, then stop, plus the cosine of 2 pi. All right, well, let's see what we get there. So the cosine of 0 is still 1. It's 1 right there. Plus the cosine of 2 pi is 1 again. It's right there. And that gives us 2. So the cosine of 0 plus 2 pi gave us 1 as an answer. The cosine of 0, stop and find it, plus the cosine of 2 pi, stop and find it, came out to 2. Their question, are they equal? No. Doesn't work. Does not work. No. So you begin to think, well, maybe it's just because we picked the quadrantals. You know, maybe it's the quadrantals that don't work. So maybe if we pick something different, we would get ourselves a really good answer. Well, let's just try something out. For the third one, it says, find your own to try with tangent. So I start thinking, how can I get something that would work out really nice that I do know? That's not a quadrantal angle that I could use it as an example. And if I made u pi over 3 and v pi over 3, adding those two together would give me 2 pi over 3. And those would be things that I could still find with exact answers. And then I could go through and show whether or not this works or not. So if we find the tangent of pi over 3 plus pi over 3, that will give us the tangent of 2 pi over 3. So we think about where that 2/3 pi would be on the unit circle. And we realize that with the pi over 3, well, if this is 2/3 of the way, this is 1/3 of the way over here. And that's 60 degrees. So this would be the square root of 3. This would be a -1 with our little 60-degree angle in here. And this would be 2. So if we're finding the tangent in that second quadrant, it's going to be opposite over adjacent, square root of 3 divided by -1, which is negative square root of 3. So that's what we get when we put the two of them together. Now, what if we do the tangent of pi over 3 plus the tangent of pi over 3? What do we get? Well, pi over 3 is 60 degrees, and we can just put that in quadrant 1. So look like this, right there. And now our square root of 3 is here, and our 1 is here, and our 2 is here. And the tangent opposite over adjacent is going to be the square root of 3 over 1, which is the square root of 3. But now I have to do it again, because I've got another tangent of pi over 3. And that's going to give me 2 square roots of 3. Very obviously, these two things are not the same. So we have negative square root of 3 and 2 square roots of 3. And just like we found out with the quantity u plus v squared, that doesn't equal u squared plus v squared. And our square root example above the exploration box, it doesn't work. It isn't going to happen. So we've seen a case where we had quadrantal angles. In fact, we saw 2 of those. And then we saw one that was just using our basic 30, 60, 90 triangle. And we realized, hey, all we really needed was one counter example. That doesn't work. But we still want a way to find answers that are perfect. We still want a way to say, hey, I can use combinations of the wonderful 45, 45, 90 and 30, 60, 90 triangles to get perfect answers. And because this has been studied for so long, of course, they found some. Sign up here. And notice we've got a big star here that says no sign change. What that means is if you're finding the sign of two angles that are supposed to be added together, you keep addition. If you're finding those for subtraction, you keep subtraction. And I always like the symmetry of these formulas because for sine, it's sine, cosine, cosine, sine. It's like you can fold it over and get the same thing on the other side. So for sine, notice for both of them, sine, cosine, cosine, sine. That's how it works. And you keep the sign of what you're trying to do with those angles. Cosine, this is where people make a mistake. Because with cosine, you have to change the sign. So notice this cosine has addition in it. Well, the formula itself is going to have subtraction. And subtraction for this cosine has addition in the formula. But this one, again, we've got this nice symmetry because it's cosine, cosine, sine, sine. So notice this. If we're talking about sine, it starts with sine, but then it's kind of oscillating. We go sine, cosine, cosine, sine, and they have that nice symmetry. With cosine, it's going to be cosine, cosine, sine, sine. Now, I say that, and you guys don't have to memorize it, because literally what I did for the test was I went ahead and took a screenshot of your green page, and I used that right before the problems that you're going to need this for on the test. But when you're doing your homework, you're going to accidentally memorize these. And some of the problems that we do count on you being able to quickly say, oh, wait a minute, this one's cosine, cosine, sine, sine. Ooh, that came from cosine. And grab those patterns off of there. So you just take a couple of minutes to look them over and realize I should be able to tell the difference between these two things. I really should. So in order to use these formulas, we need to be able to rewrite angles as a combination of all of our special ones. So the first thing I want to do before we get rolling on this too much is to start talking radians, because that's usually the piece people are a little more uncomfortable with. And think about the fact that really our special ones come from these situations, like so. And I think, okay, so when I'm working with these, and I am going to try to figure out a combination that would give me pi over 12, 5 pi over 12, 7 pi over 12. They all need a common denominator, 12. So I should really start thinking what happens when you have 1 pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, 5 pi over 12, etc. Because that's going to help me figure out which of these is going to work nicely with the ones I already know. So now we know that if we reduce this, that'll be a nice one. 2 pi over 12, that'll give us pi over 6. That's something exact. We know cosine, sine, tangent of that pi over 6 angle, and we know it exact. 3 pi over 12, well, that would also be a nice one, because that's our 45 degree angle, so that would be a good one. 4 pi over 12 would be excellent, and obviously I didn't do the rest of them on that. But it gives you a sense of the fact that the common denominator for most of these, we should be thinking 12, and how we're going to make that happen, how we can use the ones that we already know. So let's back up for a second and think degrees. It says express the angle as the sum or difference of special angles, which means multiples of 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees if we need to. And then those with radians, pi over 6 and pi over 4. And there's more than one way to do these. So think about using degrees, 30, 60, 45, 90, etc. What is a combination that you could use with addition or subtraction that would get you 15? Oh, don't use radians though, use degrees for these on the top. 30 minus. But 15 would be one of our nice ones. Freedom? 45 and 30. Now, here's the whole reason we do this. We know these exact. We know 45 degrees. We know 30 degrees. And we know them perfect. It's not like we're gonna grab a calculator and find those. That means this will allow us to figure out 15 degrees. Perfect. We will be able to do that. All right, 75 degrees using combinations of the nice ones that we know. 45 and 30. 165 is going to take a little time. So I'm going to get you a candy card. Make sure you take your packet and the writing utensil on it. You don't need a calculator or anything like that. But see if you can find one, and then when you get together, maybe your partner will have another one. Like it says, we're allowed to use multiples as well. All right, get the candy up in the air, find your partner or partners. There might be 2 groups of 3 today.
Cackle. Sorry, Jackson, I got that.
Oh, sure. Pitch it and grab new one. Oh, we might have a couple of groups of red suckers. Join a group of red suckers. Where's the other dum-dum suckers? For number 3, I have seen a couple of different answers at this point. Several people are doing this, 3 times 45 plus 30. Does that work? Check it out. 3 times 45, 135 plus 30. Okay, then what was the other one? Some of you are using addition of 3. Tell me out. 90, 45, and 30. Because honestly, this was the first one that came to me when I did this problem. You know, thinking about the multiples as we go through there. Now, I wanted you to have partners for this part because some of you are not as comfortable working with fractions as the others. So if you haven't already, go through with your partner, talk through 4, 5, and 6. I want to wander around and see what's most popular in the answers to those.
Number 1. Yeah, let's expect you put the 40 as subtraction.
But those are for numbers.
Oh. That's why I said there's for you like
power 4 minus power
But
6.
for addition and subtraction.
Power 12 minus
It depends on the formula. You've got to take a look at the formulas because they
What do you
don't all
mean?
work that way. Well, just like we said, F of the quantity plus E doesn't equal F of the unit.
Get it without using anything over 12.
Yeah, but if you're trying to find 15 degrees, wouldn't you just take half a mile of it? I don't understand. What is our goal right now?
To be able to find answers for angles that are not necessarily on the
That's pi over 6 times 1. I don't know. Okay, for this one, okay, hold on. I know these wouldn't work that way because they don't have anything that's perfect that they can multiply. Is that what you're trying to tell me? Yes. Okay. But if you have
Remember,
something
it
you
has to
know,
work for everything.
so let's say you had 135. Well, okay, hold on. Let's say you had 9. No, that's
Just
45.
focus on what's on.
4 plus pi over 6.
I'm trying to think of something that would work, but that's what you only want.
Would pi over 12 be a multiple of 4 12 minus pi over 12?
But we can't take it to the small numbers. Right now, it's going to be adding and subtracting.
So, but you can use pi over 12?
Oh, you can use all. It's going to be one of those things that. Well, we
Zero.
can find another way. 'Cause right now, what we're doing is just coming up with different ways.
Okay.
No,
Let's say you had
No.
let's say you had a 135-degree angle, okay, which is 3 pi over 2. Okay. And you wanted to figure out
overwhelmingly, it looks like pi over 3 minus pi over 4 wins for number 4. And then for number 5, pi over 6 plus pi over 4 is definitely what I saw on most papers. And then most of you realize, hey, I could just use what I used for number 4 and do addition instead and get number 6. Like so. Now this is just to show us.
yeah, it's not allowed. It's on pi over 4.
Yeah, it is.
Oh wait, hold on.
That's why I had everybody working with partners, so you can kind of reason through them together and say, is this going to work? Because most people start off saying pi over 4 minus pi over 3. And you realize, wait a minute, I'm going to give you a negative. And then you have to flip it around. Fractions are very unique. So again, these are not the only answers. You might have had some other combinations, and that's just fine. But what we want to use this for is to find exact values for numbers that don't necessarily show up on our unit circle, but we could relate them to our unit circle. So I'm going to have you work with your partners a little bit later again, but yeah, get somewhere where you can sit and write. Anyway, that would be cool. So cosine of 15 degrees, everybody said let's use 45 and 30. And that's what our new formulas are for. You know, we have some for addition and some for subtraction. So I think back and I remember cosine. Oh, that's not so hard. You do cosine, cosine, sine, sine. With one wrinkle. Cosine has one wrinkle. You remember what the one wrinkle is? You have to switch signs. That's what people usually forget. And then, here's U, here's V, so 45 and 30. And of course we realize, hey, we know these, you know. And there are two different types of people out there. There are some of you right now that are thinking about that unit circle and getting those points on the unit circle. And then there are some of you that, like me, would go back to the old triangle method here. we'll get there, either way. So, cosine of 45 degrees, what is it? Square root of 2 over 2.
Oh, okay.
Cosine of 30 degrees. Square root of 3 over 2. Sine of 45 degrees. Square root of 2 over 2. Sine of 30 degrees. Is it 1/2, everybody? Okay. So again, what some people are doing right now is they're saying, okay, this one was square root of 3 over 2. That doesn't look like a 3. 1/2. This was square root of 2 over 2. And this is a cofunction. And putting all that visual together. And like I said, some will be triangles. That's no big deal. We'll both get there. But what you have to remember with this is with fractions, it's always top times top, bottom times bottom. And so we've got square root of 2 times the square root of 3. In order to multiply two radicals, they have to have the same index. They do. So it'll be square root of 6 over 4 plus square root of 2 over 4. Now, I don't know why, but usually we don't leave that as our answer with these. It's just one of those things that throughout history, they have always written them with a common denominator. But that's exact. That's a big deal. You know, we're saying we were able to find the cosine of 15 degrees as the square root of 6 plus the square root of 2 over 4.
You want them rational?
Oh, I don't think your book does any rationalizing of the denominator for this stuff. I don't think they do. Because this is another one where historically, yes, we've always rationalized the denominator, but your book doesn't. Because remember, they said we could just use a calculator, which for me is ridiculous because this answer is going to be a nasty decimal and we want it exact. But yeah, they said it's okay to leave radicals in the denominator from now on. That's what we'll do. You know? It'll be fine. So now we found a use for it. You know, now we know exact cosine of 15 degrees. So, what else can we do with it? Good news, we can still do proofs. Yay!
Are you kidding me? We're doing proof?
You're gonna like these. You are. You're gonna like them. I know you're trying not to already. I can see it. You're trying not to. Because it's all fun. Who isn't or wants to be? Everybody does.
Everybody has to be a math teacher.
Well, yeah.
Cedar, these are simple identities.
All right.
Shh. We already have
People are all worked up because they see it says prove. Let them be worked up and then we'll just calm them down. All right, sine. That one did not go. Cosine, cosine, sine, sine. How did that one go? Sine, cosine, cosine, sine. Do we get to keep the subtraction? That we get to keep. Well, here's u, pi over 2. Here's v, x. We want to make it match the right-hand side of this thing. Well, to do that, we need to know what the sine of pi over 2 is. What's the sine of pi over 2?
0, 1.
What's the cosine of pi over 2? I like that
We have to have a cofunction.
lots.
Isn't there like a anything where it already says pi?
Well, yeah, but we have to know it works.
We already have them.
Well, now we did it algebraically too. Gosh, sometimes you just do math for fun, people. That's fun.
Cedar, I could have just said cofunction identity, cosine of x equals x.
Easy way out. Everybody wants the easy way out. Oh, wait a minute, we have one more to do. We do.
It's the same
Got
exact.
the cosine one. It's not exactly the same.
It's the same.
Oh, I did B first, huh? It's not exactly the same.
It's the same.
Nuh-uh.
It's the same. Pretty much.
Cosine. Formula. Cosine, cosine, sine, sine. But what do you have to remember?
Plus.
Pi over 2 and x. Cosine pi over 2.
0.
0. Sine of pi over 2.
1.
Oops, it doesn't look like a 1. It's all crooked. So it is the sine of x. Very cool. But yeah, we knew this because of the relationship in the triangle with the cofunctions. They're complementary. We knew that. But this is an algebraic proof that it works. So it's not a matter of, oh, they already gave us that. We already thought our way through that. It's, can you prove it? And this would be the nice way to prove it when we're doing this. So now, we're supposed to think backwards. So, we're coming up with the sine of u plus v or u minus v or a cosine of whatever. And so the first thing we do is look at this one and think, is that going to be sine or cosine for a? Yeah, because we've got sine, cosine, cosine, sine. And is it sine of u plus v or u minus v? That's right, because with sine you get to keep the sign. Well, what are the two obvious things that are going to your u and v? 22 and 13. So initially, this problem asks them to break apart what angle? 35. That was the initial problem. You'll find the sine of 35 degrees. How about b? That's cosine. Cosine, cosine, sine, sine. U plus v or u minus v? Minus. Cosine is always the opposite. What and what? So it wants us to find the cosine of pi over 12. Yeah, so working backwards, this is what you started with. Now, C, I'm going to take you through the very first step, and then I want you and your partner to work through this. Something's wrong. What's wrong? There you go. So we have to change that order in order to make it fit our formula. So we're going to go ahead and pull a -1 out of there and reverse this. And now you and your partner, give me what it was originally. Yeah. Distribute it back. You gotta go back to the original. So then it would be the original. We're just factoring -1 up. So your job. Yep.
I thought you said you were sorry. Yeah.
Oh.
Hey, of course it. Yeah.
There were a couple of little mistakes. Every once in a while, somebody just dropped the negative, and that happens. You know, we took care of it right away. The other thing was that if we have a minus here, it has to be a plus from the formula because this was cosine. And cosine, the signs always switch when you go through there. But excellent problem, followed by two more excellent proofs that we need to do. Because when something works out really nice, we want to use it. So if one of the angles in a sum or difference is a quadrantal angle, we saw earlier, hey, that's going to give us ones and negative ones and zeros and things just, boom, come down to something simple. I mean, that's what we want. So it says, then the sum and difference identities yield single-termed expressions. Beautiful. Cosine x, sine of x, negative cosine x, negative sine of x, those nice things. Since the effect is to reduce the complexity, the resulting identity is called a reduction formula. So we're going to prove this, which means we're starting off on the side that looks more complicated, which is our sine of x plus pi. And we need the sine formula. So help me out here. How does the pattern go for sine?
Sine,
Sine,
cosine.
cosine, cosine, sine. And should we use plus or minus? Plus. Sine, you get to keep that. And we need a little x and pi and x and pi. Sine of x, well, we don't know what that is yet. But we are hoping some really nice stuff comes from dealing with pi. So what is the cosine of pi? -1. What is the sine of pi?
0.
Oh, like that. Because 0 times anything is 0. So this is sine x -1, but I shouldn't write it like that, should I? Pull it to the front. Exactly. Negative sine of x. Because we want to know, this is supposed to be one term when we're doing this proof, and we were supposed to get negative sine x. So we want that out in front so we can see that. Well, this was complicated. Cosine of x plus 3 pi over 2, and then you realize 3 pi over 2, that's a quadrantal angle. This is going to be nice. So cosine of x plus 3 pi over 2. The pattern is cosine, cosine, sine, sine. But what's the issue? Yeah, we have to change it to subtraction. Change it to subtraction. Now we're going to put in our little x and our 3 pi over 2 and hope things work out nicely. And you and your partner are going to come up with the reduction of this one. The lights, you can see it.
No, 0. Alright, so what's the sign?
So it's 0 minus sine x. So Eddie, you don't get it? Oh, yeah. That's,
What's good when I was wandering around? I'd like you to 4, 3, 2, 1, 0 me on cosine and sine. Some difference. How do you feel about these? All right, looking good. Now, unfortunately, you won't be able to do all of them because we didn't do tangent.
I'd say
But
unfortunately.
go through and do any of those that have cosine and sine.
You know, you act like we care that you can't do them all.
You think y'all want to do that?
You're supposed to want to learn.
Well, I definitely don't want.
That's exactly what we're.